Lecture, D.P Roy Memorial Lecture today evening. So before we start, I request our director, Professor Trivedi, and Mrs. Monica Roy, and our speaker, Professor Kate Goldberg, to come and take seat here on the stage. Okay, thank you very much. My name is Manoranjan Guchait, and it is my privilege and pleasure to welcome you here on behalf of D.P Roy Memorial Lecture Committee. I also welcome who are attending this lecture through Facebook and YouTube channel. Today we are holding second lecture of D.P Roy Memorial Series. In TIFR, very regularly, we arrange public lectures delivered by eminent scientists from abroad as well as our country to communicate and share exciting happenings in science covering a wide range of topics. Those lectures are mostly aimed to young students, mainly from colleges and high schools in Mumbai. Now it has become more global through our webcasting. Today's lecture is one of that kind in the memory of Professor late Durga Prasad Roy, in short D.P. Roy, who was associated with the Department of Theoretical Physics of TIFR for more than 30 years. He passed away in 2017 after a very brief illness. His sudden demise left his family and many of his friends, colleagues, and collaborators in a state of utter shock. He was 76 and survived by his wife, Mrs. Monica Roy, and daughter Kollani. I think they are with us today, and two grandchildren. Professor D.P. Roy, popularly known as DP, was very affectionate with younger people, a quality which helped many graduate students and postdoctoral fellows to collaborate with him on easy terms. He was equally passionate about undergraduate teaching and very keen to spread science education among young students. With this inspiration, his wife, Mrs. Monica Roy, and family have created an endowment for conducting this lecture series for young students. We are indeed very grateful to them for their generous support. Thank you very much. DP, one of the best-known phenomenologists internationally, carried out research over a wide range of topics in particle physics, namely collider phenomenology and astroparticle physics, in particular neutrino and dark matter physics. For more than 4 decades, and he published more than 200 papers, including some very comprehensive review articles. In this lecture series, the first one was delivered by Professor Christoph Grozer from Germany in 2018 on the topics of Higgs and beyond standard model physics, which were DP's favorite research topic, one of the research topics. This year, our theme is neutrino physics, also a very interesting research topic pursued by DP. Professor Kate Goldberg from Duke University, UK, and an expert in neutrino physics has kindly agreed to deliver this lecture. In addition, Professor Goldberg has also given 2 very useful technical lectures during last 2 days and had very intensive interaction with us and our students. We are indeed very grateful to her for accepting our invitation despite having a very difficult journey. So thank you very much, Professor Goldberg. Before we proceed, I would like to invite our director, Professor Trivedi, to welcome you formally and say a few words.
Thank you, Manoranjan. Mrs. Roy, members of Professor Roy's family, Professor Scholberg, and my dear friends. Very good evening to you all. It's a great privilege for me to welcome you all to the Tata Institute for Fundamental Research. Those of you joining me here live to hear this lecture, but also on the web this afternoon to hear a very exciting lecture from a really leading authority on neutrino physics, Professor Scholberg. It's a very exciting title, How to See a Star Exploring from Deep Underground. And we look forward very much to hearing from you. I want to say a few words about Professor D.P Roy before we begin. Professor D.P Roy was in my department of theoretical physics, so I knew him very well, a senior of mine. And I still remember I think it was my first day after I joined TIFR. In those times, there was a tradition in the department that the seniors would sort of do what used to be done in college, but now at the faculty level. Namely, they used to kind of rag you a little bit by asking you a few difficult physics questions, just to make sure you knew where you were and who was who. It was fun. All in the best sort of academic spirit. I had a nice long discussion with Professor Roy, I remember, where he asked me some really very intricate questions on patterns of symmetry breaking in Higgs physics and so on, beyond standard model physics. Somewhat technical things, but I was also at that time working in particle physics and related areas. It went on for about an hour and a half, and then he left, and I didn't know how had the ragging session gone, but a day later in the evening in some social event, he met me and he said, "Sandeep, that was good, that was good." And so after that, it was always very nice with him. And later on, the thing that always impressed me about him was his humbleness. He always wanted to understand things in as much depth and detail as he needed to and could, and never was deterred by asking for all the relevant help if he got stuck on anything. And this really hit home to me with an incident I'll relate and then I'll stop. After he retired, I met him a few months later and I said to him, "How are things going, Professor Roy?" And he said, "I'm working through every exercise of Peskin and Schroeder." Now, Peskin and Schroeder is a standard textbook in quantum field theory, sort of what our graduate students, read and so on. But it came out after Professor Roy, much after, he would have gone through graduate school. Even I went through graduate school. And here he was a few months after retirement, working through every problem. And then he took out the book and he said, "This one, what do you think? Here's what I'm trying to do. Do you think I'm on the right track?" So, this really hit me. Look at the humbleness, how hard he's working and so on. That was the way he would do things, understand things very thoroughly. And even when he came many years after retirement for a seminar in the department, what always hit me was he was on top of things, always on top of things. Because he was working so hard. So I think it's been a real inspiration for me personally, and I think to all the students who came into contact with him, and I think it's really wonderful we have this lecture series endowed in his honor, for which we thank Mrs. Roy and the whole family, and look forward to today's lecture and to the lectures to come in the years to come. Thank you very much.
Thank you very much, Sandeep. Now, I wish to request Mrs. Monica Roy to say a few words about our effort and
Good evening to everybody. So we are here today for the second D.P Roy Memorial Public Lecture. Last year we had the first Memorial Public Lecture, and I would like to thank TIFR for arranging this beautiful lecture series. And they have taken a lot of pain in arranging this thing, and I would like to thank everybody who is involved in this process. I will also like my sincere thanks to Professor Scholberg for accepting our invitation and agreeing to speak on this occasion. Madam, we are really grateful to you. And my husband, Professor D.P Roy, he started his research career in TIFR in 1962 as a PhD student under Professor B.M. Udgavankar. Udgavankar is a multi-dimensional personality, and everybody knows him. In Maharashtra, he is a very well-known figure. And D.P. wrote, he learned many things from Professor Udgavankar. Udgavankar, after his death, he wrote a tribute in memory of Professor Udgavankar, where he wrote that he indebted to Professor Udgavankar on 4 counts. The first one, Professor Udgavankar advised him to work on DG-pole model. And previously, he has already published paper on some other things. And Professor Udgavankar told her that DG-pole model is relatively new in those days, and it has potentially a more interesting thing. Secondly, after advising about the field, he completely left it to D.P. Roy to devise his own problem and to solve it. So those days, there was no computer, no internet, no Googles. So one has to go to the library in 1962 and go through the papers and journals and find out problems. So he wrote that this gave him a lot of confidence in doing independent research, and later on helped him to move on to new confidence to move on to the new field without any fear. Thirdly, Professor Udgavankar is a teacher. He was involved in education quite a lot, and he was the founder of the Homi Bhabha Institute of Homi Bhabha Science Center. So he took a lot of pain in discussing the analysis, solving the writing. The writing skill he developed from Professor Udgavankar. He was very critical about it. He will ask him to correct, he will give advice, and he said, unless your writing is proper, presentation is proper, so your paper will not make any impact on the international field. Especially high energy physics is a very competitive area, and there to get the recognition in an international level, presentation has to be very good. So he learned that skill, which helped him in later life. And when he was in England, he developed it so well, that when he was in England in 1970 to 1974, his British collaborator, whose mother tongue is English, they will not write the paper. It is DP who used to write the paper. And throughout his life, I think he has written all the papers by himself, all collaboration work. Lastly, he learned from Professor Udgavankar readily to give younger research students the benefit of your experience and expertise, and while maintaining the strict code of co-authorship. Professor Udgavankar never consented to put his name as a co-author, because he used to tell him that it is your work and people will know you by your work. So this is a very rare qualities, I think. So this was the seed which put on him. He had a very successful research career for more than 5 decades, out of which 4 decades was in TIFR. 1966, he left TIFR. 2 years, he went to Riverside, University of California, 66 to 68. Then 68, we got married. Then we went to Geneva for 1 year, 68 to 69. And then Toronto, University of Toronto, 69 to 70. Then Rutherford High Energy Lab from 1970 to 74. This is in Rutherford high energy level, his career boosted. There was a very good theory group, and there were young scientists coming all over the world, and they have interact, and they used to do research paper. And then he came back to India from 1974 to 76. We were in TIFR, he was in Viswabharati University, Santiniketan, and there Professor Vissas, who is a renowned physicist from Delhi University, he got appointed at Viswabharati and he wanted to make a physics group. So from Rutherford he came to Viswabharati, and within 1 year, Professor Vissas was not happy with Viswabharati and he left for Delhi. Then DP got an offer from TIFR and he joined TIFR in 1976. From 76, he has constant correction with TIFR. He joined theoretical physics department as a reader in 1976 and retired from there on 2006. After 2006, he joined Homi Bhabha Center for his post-retirement assignment and continued there till date, that is 2017. And he was active in his research for all the 4 decades. We stayed in TIFR and immensely benefited by our stay. And this is a token for our love for TIFR to have a memorial lecture in his name. And we are really grateful to TIFR. After his death, I thought of starting this memorial series. It was my husband's desire that part of his saving will be donated for some good work. So I am really thankful to TIFR. Nothing will be as good as doing a memorial lecture in TIFR. And so I am really grateful to TIFR for starting this lecture series. And I am happy that by this way I can give tribute to my husband, at the same time contribute to the progress of science, and once a year to remind him and to celebrate science, which Professor Trivedi told in the last lecture. So I am really thankful to Professor Dige, Professor Trivedi, Professor Gabhai, Professor Guchait, and other members of theoretical physics group, and others who are technical or administrative staff who were involved in this process of launching this series. My thanks to Professor Solberg once again for coming and giving us lecture. It is very nice to know you, and hope we'll come again for this series lecture. Thank you all, and once again, and thanks to everybody who are present today. That's all.
Thank you, Mrs. Roy. And thank you very much for your attention. Now let us welcome our speaker. So I invite Professor Dige to welcome and introduce our speaker. Professor Dige.
Hi, welcome to everyone. It has been my pleasure to know Professor Kate Schulberg for many years, and it's quite appropriate that she gives this lecture, because 2 of the passions of Professor D.P. Roy were colloidal physics and neutrinos. The first lecture that happened last year was in colloidal physics, and this time we get somebody who has had a very nice career in neutrinos. So Professor Kate Schulberg, she is the Arts and Sciences Professor of Physics and Bass Fellow at the Duke University. Her bachelor's was from McGill and master's and PhD from Caltech. Then she was in Boston University as a research associate, in MIT as a faculty, and now she is in the Duke University. She has worked on many neutrino experiments, starting with Super Kamiokande and macro, and currently she is the spokesperson of the coherent experiment, which looks at coherent scattering of neutrinos on nucleons, and she is also a part of the ambitious so-called DUNE experiment, It's a deep underground neutrino observatory that's going to be built in the US. Kate has received the DOE Outstanding Junior Investigator Awards, NSF Career Awards, and is a fellow of the American Physical Society. She also coordinates the so-called Supernova Early Warning Network, about which she will tell us in her talk. Kate has been here for last couple of days, and in fact, every day she has been giving at least one talk, talking to students, postdocs, and faculty members here. And I'm sure that even after her talk, she will be happy to take questions and talk to you when we have our tea there. So with this, I finish my introduction. Let me welcome Kate again. And to welcome her formally, let me request our director, Sandeep Trivedi, to give her a memento. Yeah.
Okay, now let us begin our lecture today. So, Kate, floor is yours.
Okay, thank you. I would just like to first express what a great privilege and great honor it is to give this lecture. And I'm sorry that I myself was not able to know Dr. D.P Roy, but I would like to try to make this lecture consistent with everything that I've heard about his excitement for science and his desire to share that excitement with others. So let me tell you about some science that I'm excited about, and I hope you will also be. I want to tell you how to see a star explode from deep underground. And I'll first start by telling you about neutrinos, since the way you can see a star explode from underground is via the emission of neutrinos. And neutrinos are one of my favorite particles. I guess also Dr. D.P. Roy's one of his favorite particles. They're the so-called ghostly particles. They're particles that basically go through everything almost all of the time and are very hard to detect. And just to give a very high-level introduction to why I'm interested in neutrinos, it's really I'm actually not an astrophysicist, I'm a particle physicist, and I'm interested in understanding the nature of energy, matter, and space and time, which I think is also the mission of TIFR, really on the very largest scales and on the smallest scales. And the questions that we're after are what are the particles, the fundamental particles that make up the universe? How do they interact with matter, with each other? And how did the universe come to be the way it is? And neutrinos actually touch on all of these things. And here's our current best picture. This is called the standard model of particle physics. These are the fundamental particles of nature. There are quarks. This is a very delicious version in cupcake form. There are quarks here, which are make up protons and neutrons, for example. And then there are leptons, which are lighter particles. This name lepton comes from the word, a Greek word, I think, that means light. And there are familiar particles like the electron, and then there's a heavier version called a muon, and a yet heavier version called a tau particle. And each of these charged leptons, these have electric charge, each of these charged leptons have partners that are neutrinos that have the same flavor. So we call electron, muon, tau is called flavor. The neutrinos have the same flavor as the electron, muon, tau. There's 3 kinds of them, and they also come in anti-kinds, antimatter versions. Nu E bar is an antineutrino, nu mu bar is an anti-muon neutrino, and nu tau bars. And then there's other particles, there's bosons. These are the fundamental called fermions. And we know about these particles, the quarks and the electron, we know about these from collider experiments, and we heard, I guess, last year, the lecture was about collider experiments and Higgs particle and so on. And so here, this is colliders help us know about these particles. But neutrinos are also part of the picture, and they're very strange. They have very weird properties, and one of those properties is that their mass is extremely tiny compared to the other particles. And just as an example here, if an electron, and electrons are very common particles, they're familiar parts of atoms, electrons, and of course they're very tiny light particles compared to nuclei of atoms. But if an electron is an elephant, then a neutrino is a mouse. They're really, really tiny masses. The mass of an electron is about 500,000th of the mass of a neutrino is about a 500,000th of the mass of an electron. So they really have extremely small masses, and that's weird, and that's something that is not really understood why that's the case. Now, the other major thing about neutrinos is that they interact only via the weak force. We know in the standard model of particle physics, we know of four forces. One of them doesn't really work in the standard model, but we know of four forces of nature. There's the strong force, which is what holds nuclei together. There's the familiar electromagnetic force, and then there's this weak force, which is responsible for nuclear decay, and neutrinos only interact by weak force, and that is strange. And the reason it's a weak force, it's called the weak force for a reason, the weak interaction for a reason. It's basically if a particle interacts by the weak force, it hardly interacts at all. The force it's weak. It doesn't. A strong force would mean that a particle interacts a lot. A weak force is a particle that doesn't interact very much at all. And just to give you an example, electromagnetic force, which is much stronger intrinsically than a weak force, a photon, a particle of light, interacts via electromagnetic force. And if you take a photon and you try to shoot it through material, a gamma ray is a form of photon which is famously penetrating. It will go through matter compared to other particles, other wavelengths of light. It will go through a lot of matter. So if you take a gamma ray of a particular energy range, it will go through maybe 20 centimeters worth of carbon, which is very penetrating for a photon. If you compare that to how far a neutrino will go in matter, a neutrino of similar energy will go a light year. It will actually go the distance that light will travel in a year. It will go an enormous distance in carbon. Which is really, before on average it will interact. So this is really a very, very weak interaction. And in fact, a neutrino could, just saying this in another metric, a neutrino could easily travel, this is a higher energy neutrino, could easily travel through 100,000 Earths before it would typically interact at all. So neutrinos basically just go through everything. They just zip right through you. Here's a cartoon. A neutrino will just go through any matter very easily, just like a ghost. That's why they're called the ghostly particles. And neutrinos are everywhere. They are produced in the sun. They are produced in radioactive decays, so they're coming out of the Earth, radioactive elements in the Earth. They're produced in cosmic rays in the atmosphere. They are basically everywhere. If you look at the sun, if you put your hand up to the sun, it's about 1 trillion neutrinos per second coming from the sun to you. And it just goes right through your body, goes right through your hand. So that's what it means to have a weak interaction, and that's a very weird property to have for a particle, and we actually don't fully understand the reason for these, the very small masses and the very weak interactions. It's a very exciting topic of research. So you might ask, how do you actually detect neutrinos? And so this probably dates me, but this is Geordi LaForge from Star Trek: The Next Generation. And he had, in this science fiction show, he had a special visor that allowed him to see neutrinos. And I've always really wanted to have that visor. But unfortunately, there is no such thing that we know of. It doesn't work to have such a visor. You actually have to build a detector in order to see a neutrino. And how do you actually do it? Well, neutrinos rarely interact, but rare doesn't mean never. They will sometimes interact with matter. They will sometimes have a collision with matter and create a charged particle. And a charged particle is the kind of particle that you can detect and see in a regular particle detector. And so that's how what we have to do is we have to build detectors that are big enough to see the occasional interaction of a neutrino. And it's challenging. It's hard to make these detectors big enough, but it's possible. And there are many detectors worldwide. And so here's one that I work on called Super K that's filled with 30 kilotons of water, actually total about 50 kilotons of water, so enormous amounts of water. This is another detector that's filled with hydrocarbon. Here's another one that is made of iron. And existing detectors have to be, the detectors that exist today are of sizes typically of order kilotons to tens of kilotons. So these are really, really enormous detectors that are required to see these rare interactions. You just have to make them so big in order to catch even a few of the ghostly neutrinos. And it's not only that the detectors have to be big, there's another problem, which is that we're surrounded by cosmic rays coming from the atmosphere, from particles coming from outer space that are colliding in the atmosphere, that are making more particles. And right now, we're sitting in this room in a shower of cosmic rays. In fact, if you put your hand out, there's probably about 1 cosmic ray muon per second going through it. And what that means is if you're looking for very rare interactions of neutrinos, that's hard to tell apart from a constant rain of cosmic rays coming down on you. It's basically a background that will shine more brightly than the rare signal that you're looking for. And for that reason, you can't have a detector on the surface very easily if you're looking for neutrinos because of all the cosmic rays. And so what that means is you have to put your detector underground where there's a very deep layer of Earth in which all the cosmic rays will basically bury themselves and die out before they get to your deep underground detector. And so that means that all of these big detectors, in fact, all of these that I showed you, the ones that exist today that are kiloton scale, they all actually are buried deep underground in order to be shielded from the constant rain of cosmic rays. So that's another difficulty, that's another huge challenge in building a neutrino detector. It have to be as much as, you would like to be as deep as you possibly can, but usually at least 1 kilometer or something underground in order to get away from the cosmic rays. Okay, so that's neutrinos. So now let me tell you about supernovae, which is another thing that I love. So supernovae are energetic outbursts that basically completely blow up a star. And they are very, very brilliant events, very, very luminous events. And if you take a galaxy, a supernova that occurs just from one star in a galaxy can shine as brightly in photons, in light, as the entire galaxy for a brief time. And I have a little asterisk on there. There's a little caveat because, in fact, very large galaxies might be brighter than a supernova. A famous astronomer once took me to task for making this statement. But a small galaxy certainly is less bright than an actual supernova. So this is an example. Here's a supernova that's coming from just the explosion of one star in the outskirts of this galaxy that is almost as bright as the galaxy itself. So these are incredibly bright, luminous events, and they can last for days and even months. It takes them to die down and become dim again. So there's different kinds of supernovae, and they actually occur by different mechanisms. The physical mechanism that causes this bright explosion, there's actually one kind that is like a giant thermonuclear explosion. It happens when mass is accreted onto a star from a nearby star, and that makes it contract and heat up, and then it will create a fusion explosion, and then it will blow up. I'm actually not talking about that. Those supernovae are also very interesting. They serve as standard candles for knowing how far away things are. The kind of supernova that I'm going to talk about here is the kind that makes an enormous burst of neutrinos, is a type 2 supernova. There's also technically a few other types. And what happens, the physical mechanism behind this kind of supernova, is the gravitational collapse of a massive star that has reached the end of its life. And so what happens, the sequence of events, is if you have a very massive star, it's burning nuclear fuel. Stars produce their energy by burning nuclear fuel. And as they get, if they start big enough, maybe about 8 times the mass of the sun, then they will ignite fusion reactions of heavier and heavier elements as they proceed in their evolutionary life, which is tens of hundreds of thousands of years. And you end up with kind of an onion shell structure where you have heavy elements being burned inside and light elements being burned on the outside. When the burning comes to iron, iron can't burn anymore. It's kind of a nuclear ash. Once the iron core of the star gets big enough, it reaches what's called the Chandrasekhar mass. This was Professor Chandrasekhar who first calculated how much that was. And it can no longer hold itself up against pressure because it can't burn anymore. It can't, it's got weight pulling down on it, and the heat of the burning is not holding up the outer layers of the star anymore. And it will collapse dramatically and very, very quickly, and it will scrunch down to very, very dense matter. The protons and electrons, it's so dense that protons and electrons, which are normally different parts of an atom, will actually bind to each other and create neutrons. And it's amazing pressures that have to occur for that to happen. And that emits neutrinos, and it creates neutrons. And what results is a very dense neutron star, a star made entirely out of neutrons, made of ultra-dense matter. And that's what's called a compact remnant. And it might even create a black hole. If there's enough matter accreting onto a neutron star, it can actually collapse even further and form a black hole. So really tremendous exotic conditions occur. And in this process, there can be a bounce. So the matter falls down, squishes down, bounces back out, creates a shock wave that then blows up the entire star. And at the same time, it's producing copious amounts of neutrinos. And so what the observational result is, if you're a neutrino physicist, is that in your detector, you will see a brilliant burst of neutrinos in about 10 seconds. And it will be visible in neutrino detectors all around the world, accompanying this really dramatic event of the collapse of a star and then the subsequent explosion, and possibly black hole formation. And actually, if the black hole forms, there may not be an explosion at all. It may just, everything will fall in, and you get a short burst of neutrinos, but in fact, no brilliant explosion. And so that is actually also a way you could see a black hole being formed in the neutrinos without a supernova, which would actually be very interesting to observe. Now, if you're a neutrino physicist, there are pros and there are cons. So this weakness of the neutrino interaction, it's a blessing and it's also a curse. And so this picture is from doing a Google search of ghosts escaping. So that's the meaning of the picture. So the neutrinos will bring information because they just go through everything. They go through the stellar envelope. They just leave the star immediately. They bring information from very deep inside that you would never be able to see from photons because photons interact and they never get out from inside a big, heavy stellar envelope. And so that's the blessing of neutrinos, is you can actually see inside a super dense object and learn about what's happening inside a really exotic dense object. You can see the black hole being formed. But the curse is, at the same time, the neutrinos interact so rarely that you have to have these enormous detectors and underground detectors. You have to go to enormous effort to actually see them. So it's kind of pros and cons. So now let me make a kind of physical argument about why you get neutrinos from core collapse. And So you may remember that gravitational energy, if you drop something, gravitational energy turns into kinetic energy. And this is what you get when an object falls. You know, if you drop a piano, it has gravitational potential energy, and it turns into, it starts falling faster and faster. That turns into kinetic energy, and when it hits the ground, you get thermal energy, you get noise, you get a big crash when it actually hits the ground. And this same thing happens in a collapsing star. So in a collapsing star, the star is basically falling inward, spherically. All the outer layers of the star are collapsing. And that energy has to go somewhere. So it's gravitational energy turning into kinetic energy, energy of motion. And there has to be a crash, and the energy has to go somewhere. And because the neutrinos can escape, because they can actually get out, the neutrinos have energy, and when they escape, they are liberating energy from the star. They're taking energy away because of the weakness of the neutrino interaction. And so what that means is because they can leak all the energy away from the star, basically all of that energy of the crash, of the fall of the star, leaks away in neutrinos. And all of the energy created by the formation of this baby neutron star leaves the star within about 10 seconds. And so it's a very sharp, brilliant, bright burst of neutrinos. And it's almost all of the energy. And there's only 1% of the energy left to create that explosion. And you remember I told you that that explosion can shine as brightly as a galaxy, or a small galaxy anyway. The neutrino energy is more than 100 times the brilliant energy of a supernova. So it's an enormous burst of neutrinos that comes from a core collapse. It's really an amazingly dramatic event. If you had Geordie LaForge's visor, you would be completely blinded by the neutrinos that come from a core collapse. And so understanding how this happens is actually a topic of a lot of research now, both theoretical research now. Actually, this is not, I'm an experimentalist. I actually don't do this theoretical research, but I certainly follow it. There are a lot of very sophisticated computer simulations to try to understand exactly how the burst happens, exactly how the collapse happens, and how it turns into this enormous explosion. And really understanding all the physics and the astrophysics of this is a really major topic of study for a lot of theorists. And one thing that they have learned doing these, so these are pretty pictures from these computer simulations of exploding stars, and what they've learned is that neutrinos are intimately involved in the process, that neutrinos have energy, and it's true they mostly escape, they leave the star very quickly, but it's also true that they do sometimes interact, and they may actually interact enough to affect how the explosion happens. And so it's really important for us to understand the properties of neutrinos so that we understand how these collapses happen. So this is a very, very exciting thing. Okay, and so a supernova has happened before and was actually observed in neutrinos. This has happened once in history, which was a bit more than 30 years ago. This was supernova 1987A. This was a famous supernova. It happened not in our galaxy, but in a small galaxy called the Large Magellanic Cloud, which is outside of our galaxy. It's about 5 times farther away than the center of our galaxy. And this is the famous picture of it. This is before and this is after really bright supernova in that nearby galaxy. And there were about 24 neutrinos that were observed in 2 detectors made of water from this supernova. And so this is an enormous, had enormous impact in particle physics and astrophysics. It really told us that we have a good understanding of how that collapse happens and how the neutrinos are produced. In fact, there were many more papers. There were a couple dozen neutrinos, and there were hundreds of papers written about them. So this is really was a major event. But at that time, in 1987, there were only relatively small neutrino detectors running. They were about 3, one was about 3 kilotons, one was about 8. And we now have much bigger and better detectors. And if the same supernova went off today, we would do a much better job in gathering the neutrino signal from it. And in fact, here's a picture. These are my colleagues. And this was 2 years ago that we had a birthday party for the supernova, and that's my colleagues are singing happy birthday to the supernova in February 2017. Okay, and you might ask, well, how often does this happen? And so here's a picture of our local neighborhood. So here's the Milky Way galaxy where we live. There's some small galaxies around. There's the large and small LMC is the Large Magellanic Cloud. There's a Small Magellanic Cloud. These are visible in the southern hemisphere. There's some other little galaxies around. This is the Andromeda Galaxy. Some of you may have seen it. That's also visible by naked eye from Earth. It's about 700 times, it's about 70 times farther away than the center of the galaxy. But it's a quite large galaxy here. And so this here is our local neighborhood. This is this circle here is the circle in which we would expect to see a supernova about every 30 years. And it's also true in Andromeda, we should see a core collapse supernova about every 30 years. So this is an event that happens rarely, but it's on the timescale of a human lifetime that you might be able to see a supernova. It's not unreasonable to think that a core collapse supernova could happen in your lifetime. And it's not something that happens every 1,000 years. It's something that happens maybe every 30 years or so. Okay, so what are we going to learn? This is probably the most complicated slide I have. So what are we going to learn from the next time a galactic supernova blows up in our galaxy? And there's just a tremendous amount that we would learn. It would just be amazing. We would learn about the core collapse. We would learn about how does this explosion happen. We would learn how does a neutron star form and cool, because you can actually kind of X-ray the supernova with the neutrinos. The neutrinos are bringing information out from very deep inside. We could see if a black hole formed. That would cause the signal to sharply cut off after about 2 seconds. As the black hole formed, it would be a very distinctive signature, so we could see if a black hole formed inside a supernova. That's something we weren't able to do with 87A. We could tell if there's something exotic that might have been formed. And also we can learn about how the elements that we think that some of the elements, at least some of the elements that exist on Earth were made in supernovae, and we could learn about how those elements are formed by looking at the neutrino signal. We could also learn about neutrinos, and I'm actually a particle physicist. I'm not really an astrophysicist. I just kind of dabble in astrophysics. But I'm also interested in the properties of neutrinos, and a supernova is a huge burst of neutrinos that we could actually use to learn about the properties of neutrinos themselves. We can learn about their masses and how they change flavor, which is I didn't mention it, but that's a very important property of neutrinos. And we also may be able to learn if there's new physics beyond the standard model, which is something that all of us in particle physics are interested in. Is there some kind of new particles or new interactions? And we may be able to tell that from the burst from the supernova. We may be able to see evidence, imprints of exotic physics there. So there's an enormous amount to be had. And this is kind of a virtuous circle in that the more we know from observations of the supernova, the better we will be able to learn about neutrino physics. And the more we do experiments and learn about neutrinos on the Earth, the better we can learn about the astrophysics. And so it's really, each side of the astrophysics and the particle physics is supporting of the other side. And one other thing I'm going to come to at the end is there's also an early alert, and that is because the neutrinos will come out first. And we will see neutrinos before we see the light from the supernova. And that's not because neutrinos go faster than light, as there was a erroneous hint some years ago. It's because the neutrinos get out right away. They just exit the supernova immediately. They all come within about 10 seconds or a few tens of seconds. But the light will take possibly a long time to get out of the supernova because photons interact with matter, and they have to make their way out of the envelope, and that takes time, and it could take hours, it could even take a day if it's a star that has a huge amount of mass. And so what that means is if detectors see a burst of neutrinos, they can warn astronomers that, hey, a supernova is about to blow up, you better go look for something. And so that's an important function that is possible with neutrino detectors. We can actually alert astronomers that a core collapse is about to happen. Of course, there might actually be no supernova. That's interesting in itself, but certainly astronomers want to go look to see if they can see a supernova. So now let me tell you about supernova neutrino detectors. There's a bunch of different kinds of them, and they come in different types, made of different materials. So there are detectors that are made of water, and that water can either be in liquid form or solid form. I'll say a little bit about both. They can be made of a material called scintillator, which is hydrocarbon, and it's like oil of some kind. It's a material that emits light when particles lose energy in it, and so that's called scintillator. There's also argon. And argon is also a scintillator, and it's also a kind of detector where you can observe energy loss of particles by putting an electric field on it. I'll say a bit more about that. That's actually what DUNE is made of. And then there's also some detectors that are made of materials like lead. And most of these detectors have a day job in the sense that because a supernova only happens we think it probably only happens every 30 years, it's actually hard to get funding to build a really big detector that will run for 30 years, or maybe it will be 50 years or 80 years and not see anything. And so almost all of the detectors we have today are actually built for other purposes in neutrino physics other than looking for a supernova. For example, looking for solar neutrinos, looking for neutrinos from the atmosphere, looking for neutrinos that are coming from a beam. We can actually create neutrinos and send them in a beam underneath the Earth. They just go right through the Earth, and then we can observe them in the detector. And so there's actually a whole industry of neutrino experiments that are aimed at understanding the properties of neutrinos, also properties of the sun, and so on. And these detectors are built with those purposes in mind, but it turns out that they are also, by virtue of their neutrino detection properties, they are also sensitive to the burst of neutrinos from a supernova. So almost all of these detectors I'm going to tell you about are really, supernova is kind of their hobby. But of course, if a supernova happens, it will become their main job. And so here's one kind of detector. This is a water Cherenkov detector. This is a detector that's made of ultra-pure water. This is what Super Kamiokande is. So it tends to be a big volume of very pure water. And the way you can see a neutrino is that when a neutrino interacts, it makes a charged particle. And then that charged particle creates light in the water via what's called the Cherenkov mechanism. And then that light is detected in very sensitive photon detectors. And so here's a little bit more about Cherenkov radiation. It's what happens if a particle goes faster than the speed of light in a medium. Now, a particle can never go faster than the speed of light in a vacuum. But in a medium, the light is slowed down by a factor of the index of refraction. So in a medium, you can have a particle that is actually going faster than the speed of light in that medium. And what happens when the particle goes faster than the speed of light in the medium is you get a shock wave. You get kind of a shock wave of light. And it's actually kind of like, so this is not a particle, this is a fighter jet, but this is a visualization of a shock wave of sound. So when you have an aircraft that goes faster than the speed of sound in a medium, you get a sonic boom, you get a shock wave. It's the same kind of thing with light for Cherenkov radiation. So you get a kind of a shock wave of light, and it makes a cone in the direction of the particle traveling. And that's actually, if you've seen pictures of nuclear reactors and they're glowing blue, that's what, that light is actually mostly in the UV and the blue wavelength, and so that's what this light is. If you see a picture like that, it's Cherenkov radiation that comes from charged particles moving in a water surrounding a reactor core. So it's a kind of a blue glow in a cone, and you can actually image this cone of light. And so let me tell you now about Super K, which is really currently the only big water Cherenkov detector. This is a detector I've been working on since 1996. I've been in the collaboration since then. It's got total of about 50 kilotons of ultrapure water in this inner vessel, which is 40 meters high and 17-meter radius, so it's enormous. It's really huge. It has these light sensors lining the inside. These are photomultiplier tubes. These are sensors that are sensitive to even a single photon of light. So they're super, super sensitive to light, and they're huge. They look small on this picture, but they're about that big. They're very large. And there's also a detector on the outside, and that's to remove cosmic rays. If you have a cosmic ray that comes in, it will make light here, and then it will make light on the inside. And you know, because there's a track of light, you know it's a cosmic ray. A neutrino will seem like it comes out of nowhere. It will interact inside here, and it will make Cherenkov light inside the detector only. And this detector is underground. It's about 1 kilometer underground. It's in a mountain in Japan. It's actually in a mine in Japan, and that's to get away from the cosmic rays. But even at that depth, we still get about 3 cosmic rays per second slicing through this detector, and so we have to remove those, and so that's an experimental challenge. And this is you can actually just drive into this. This is where we eat lunch over here, and this is where the electronics is on the top of the detector. Here's a picture. This is a famous picture of Super K when it first turned on. These are the phototubes. These are the light sensors, and this is water. These are people in a boat. They're cleaning the phototubes as the water level is rising and the detector is filling. This is another pretty picture during refurbishment. So if a supernova happens, Super K will see something like 10,000 neutrinos within 10 seconds or a few tenths of seconds if a supernova happens at the center of the galaxy. So it will see an enormous number of neutrinos all at once. In fact, so here I have a simulation of this. So this is a Super K detector. This is what we call event display. And so what this is an unrolled view of the detector. So it's a cylinder. And so what this is a projection. So this is, imagine you take a can and you cut down the side and you open it out so it's flat, and then you take the top and the bottom and you lay them up here. So this is that kind of projection. And each one of these dots on here represents one photon sensor. And this is an outer detector. So here, if there's not a lot of dots on there, that means it's a neutrino interacting on the inside of the detector. So now let me run the simulation. Oops, I hope this works. Oh, not working. Okay, let's try this. Okay, there we go. There's a simulation. So this is what a supernova would look like in Super K. It would just suddenly create a whole burst. The whole thing would light up like a Christmas tree. It would be a brilliant event over about 10 seconds. And what you can see here, these are the distributions. This is the energies you would see. This is actually where they point. I'll say something about that. This is actually a sky map that shows you the direction, the overall direction of where the supernova would be that you can see from the neutrinos. So I'll do that one more time. There we go. Bam, there it goes. It's a whole bunch of Cherenkov rings all on top of each other, all within about 10 seconds. So it would be this would be a very distinctive event. We would see this immediately and very cleanly in Super K. Now let me say a little bit about pointing. So if you're an astronomer and somebody wakes you up in the middle of the night and says, hey, a supernova just happened, you're going to be pretty frustrated if they don't tell you where it's going to happen. So of course, knowing a supernova is going to happen is a good thing, but if you're an astronomer, you really want to know where on the sky should I look to see, to try to find a supernova. And it turns out that neutrinos can tell you a little bit about that. It's not the greatest, but we can provide some information about where on the sky the supernova is. And we can do that because some of the neutrinos will kick electrons, and then the electrons will then give you a Cherenkov ring in the direction that they're kicked in, and they remember that direction. And so if we look on the sky where those events are coming from, we can see that, hey, there's a blob over there. That means that the neutrinos are coming from the opposite direction. And so we will be able to tell astronomers within about 5 degrees, that's something maybe 10 times bigger than the size of the moon, so it's not a tiny spot in the sky, but we will be able to tell give some information to the astronomer woken up in the middle of the night, hey, that's where a supernova is going to happen. Okay, now Super K is continuing to run. It's been running since 1996 with some interruptions, but is now in a new phase. There's actually a planned upgrade for Super K. It's actually a different experiment, even bigger detector. So this detector is something like 174 kilotons. So it's a scale up of more than a factor of 10 size of the detector. This is called Hyper K, Hyper Kamiokande, and something like half a megaton of water. And this detector would see more than 100,000 neutrinos within 10 seconds from a supernova. So this would be an enormous sample of neutrinos. It would be absolutely fantastic to see a supernova in Hyper K. Okay, now there's one other kind of water detector, and this is actually using solid water at the South Pole, where there's an enormous layer of ice. And there's a detector at the South Pole that is called IceCube, where they have photosensors, photomultiplier tubes, that are suspended in long strings in the ice. And this is actually covers a volume of about a cubic kilometer. So this is an enormous detector. And the nominal purpose, the day job of this detector, is actually not supernova neutrinos, but to look for really high energy neutrinos that come from very exotic, distant astrophysical sources. So things like active galaxies and gamma ray bursts and really different kinds of astrophysical objects. And actually that's what this is a picture of, is a very high energy neutrino lighting up a bunch of the phototubes. But it turns out you might think, well, okay, the supernova neutrinos are much lower energy than this, and you might think that it's hard to see them in a detector like IceCube, but in fact they can see it, and it's actually a very clever method. The idea is that there's interactions of neutrinos in the ice over 10 seconds, and they create Cherenkov photons that give you this glow. So there's a glow, there's a blue glow in the ice that happens over 10 seconds, a kind of diffuse glow, and the phototubes can actually pick up this diffuse glow and see and track the time structure of the supernova over that glow. And so that is actually a really cool application of IceCube. It's actually using the detector in a way it actually wasn't designed for, but it would be able to see a supernova as well. So that would be really fantastic. Let me say a little bit about scintillation detectors. These are detectors that are made of hydrocarbon, so that has carbon and hydrogen. It's usually some kind of oil and sometimes has dopants in it. And these are materials that create light when particles leave energy in them. And there's a bunch of these different kinds of detectors worldwide. They tend to be about kiloton scale. There's one planned for the future called Juno, which is in China, which is 20 kilotons, so that will be 20 times bigger than the existing ones. So this one, there's one called Cameland in Japan, this one is Borexino in Italy, this is Snow Plus, this is in Canada. There's a surface one, which is, it's got a lot of cosmic rays in it, in their signal, but they could still do something. This is one also in Italy, and then Juno is the future one. And so these are, tend to be very, lots of light. You get a lot of photons, much more than Cherenkov, and it give very good measurements of the energy. So these are also really great detectors for seeing a supernova. Then this is what I've been working on recently. This is a liquid argon detector. This is a detector that is made of, it's cryogenic, so you have to liquefy argon, which is normally a gas at room temperature, so you have a, but it's clear, it looks like water, but it's about 1.4 times heavier than water. And so you have a huge vessel, so the idea here is you have a huge vessel of liquid argon, and when a particle goes through, it leaves a little track. It will ionize, it will tear off electrons from the atoms in the argon. And if you put a really large electric field on it, you can drift that charge. The charge will move in that electric field, and it will make an image of the track of the particle. And you can tell from the time that that charge allows, you can actually make a picture, like a 3D picture of the track that the particle leaves. And this is something that can be exquisitely done in this kind of detector. There's also light as well that comes from scintillation, so you can get that kind of signal too. So this is really a very fine-grained image of particles. So it's really attractive to particle physicists. And there have been several in the past. There was one in Italy called Icarus. There's a couple, one that's been running for a while called Microboon in the US near Fermilab. There's one that will be turning on soon, also near Fermilab. These are fairly small. These are less than a kiloton, so about 200 tons for this one. But the one that is for the future that there's a big effort to work on in the US is called DUNE. It's called the Deep Underground Neutrino Experiment, and it's 40 kilotons of argon, so a really enormous scale up of this. And the day job of DUNE is actually supernova is an important goal, but the day job is it actually looks at neutrinos that are created at Fermilab near Chicago and sent 1,300 kilometers underground and observed in the FAR detector in South Dakota. So that's a 1,300 kilometer trip that the neutrinos will make underground. They just go right through the ground and then they're observed in the FAR detector. And the purpose of this is to understand the properties of neutrinos, to understand how they change their flavors, which we actually hope will tell us about why the universe is made of matter and antimatter, but that's a different story. So that's kind of the day job of this detector. But we also expect lower energy neutrinos. We expect thousands of them during a supernova. And in fact, the reason that it's so exciting to have this in argon is that these experiments that I told you about before, the scintillation and the water detectors, they're actually sensitive mostly to antineutrinos of electron flavor. And DUNE detector, argon, is sensitive to electron flavor neutrinos. The burst from the supernova comes in all the flavors, and we want to see all the flavors if we possibly can. And what DUNE will do is it will allow us to see the electron flavor part of it, which is actually a really exciting for understanding the physics. When the neutron star is formed, the electron and the proton squeezing together to make a neutron makes an electron neutrino, and so we could actually see that explicitly. We could see the neutron star being formed if we have access to electron neutrinos. So that's a really, really exciting thing, and we would see thousands of them in these enormous modules of liquid argon underground. So here's a picture of what the underground excavation would look like. There's different halls. Each of these, there will be 4 10-kiloton modules of liquid argon. This is actually a higher energy event, but you get this really exquisitely precise particle tracking in this kind of detector. So it's a really, really attractive detector. Supernova neutrinos are actually lower energy. They are not. This kind of picture is of a high energy neutrino. Supernova neutrinos are actually quite a bit lower energy than those. They tend to be much more modest little tracks, so we call them stubs and sparkles. So what you would actually see in the detector is like a little worm like this, a little stub, but sometimes some people call them crummy little stubs. I like to call them cute little stubs because I love them. So here's what you get, and then you get a bunch of, this is a gamma ray will then make little blips around, and you could get, what you get is a little stub that is surrounded by a bunch of little blips that will be a distinctive signature of this kind of event. So this is what we would see thousands of these in DUNE if a supernova happens at the center of the galaxy. And I have to say, sometimes these neutrino detectors collaborations are kind of competing with each other. There's, Hyper-K and DUNE are these 2 really big programs, one in Japan, one in the US, and the physicists on those experiments it's a friendly competition, but they're kind of competing with each other to do the physics. But I have to say, supernova physics is not like that. It's not competitive. It's really collaborative because the different detectors are sensitive to different flavors, and it's a situation where the more you have, the more information you get from a supernova, the better the science comes out. It's really something where the whole is more than the sum of the parts. You really want all the flavors coming from the supernova, you want all the information, and so it's no competition. It's basically everybody has to gather all the information they possibly can from a supernova happening in the galaxy. And just as another example of collaborativeness, of why, how, if the different experiments really get together and share information, it gives you something that is more than the sum of the parts. So this is the Supernova Early Warning System. And so this is a system that's designed to wake astronomers up in the middle of the night. The idea is that if you have a burst of neutrinos, you have a pretty good idea there's a supernova, but in real life, individual detectors can be kind of noisy, and you can have a burst, and sometimes it's a fake one, so it can be due to some calibration, or due to some mistake, or due to a big muon, or something like that. So it's not always true that every burst you see in a detector is always a supernova. However, if you have two detectors on different sides of the Earth seeing a burst at the same time, then you know something is up. That is not likely to be some sort of calibration or some sort of mistake. That is going to be very likely some kind of galactic signal. And so this is why we have this system called the Supernova Early Warning System, is that it's set up so that individual experiments can send their datagrams. If they can automatically, they don't need a human involved, they can look at the data and look for a burst of events. If they see a burst of events, then they send a datagram to a central computer, and that central computer can sit there and wait and say, well, I see two things that happened at the same time within 10 seconds, according to the timestamp, and that is a very high probability it's a supernova, and that central computer can then send an alert out to astronomers. And so that's what we have set up. We actually have now 7 detectors that are part of this network, and in fact, it's basically all of the detectors that are sensitive to a supernova burst that exist today. And so that includes Super K. This is a lead detector at Snow Lab. This is CAMLAND in Japan. This is LVD in Italy. This is Diabei. It's actually a surface detector, but has multiple detectors to suppress background in China. This is Borexino in Italy, and that's IceCube at the South Pole. And we have all of these detectors in the network. They're all individually waiting for a supernova burst. If they see something, they send a datagram to our server, and if that server sees 2 or more within 10 seconds, it sends out an automatic alert to astronomers. And this has been running smoothly for more than 12 years now. It's been automated since 2005. And we have not seen any supernovae, but that's apparently because there haven't been any. So that's unfortunate, but we're still ready for another one. So you can actually here's just another graphic showing where all these detectors are located in the world. And you can sign up. And so we actually think that amateur astronomers may be able to help pinpoint where the supernova is. Most of these detectors aren't going to be very good at actually pinpointing the location of the supernova. So Super K is able to do that. I showed you how Super K can actually use the signal to point back to maybe 5 degrees or something on the sky. But that signal may not be available instantly. That information may not be available instantly. And so what that means is that we may get an alert and not know where the neutrinos are coming from, not know where the supernova is. And so we actually have amateurs, astronomers, who are ready to receive this. And amateur astronomers may be able, because amateur astronomers actually know the sky very well, may be able to find the first light from the supernova and propagate that to the professional astronomers. And so that's a hope that we have to try to find the first light of the supernova. It will be if we actually get this alert, it will be a hunt to find the supernova. There may be no supernova, which is exciting in itself, but it's actually very exciting to be able to see the early turn on of the light from the supernova. So you can actually yourself go to snooze.bnl.gov and sign up, and you can be on the list to get the early alert from SNOOZE. So basically anybody can sign up to be part of the SNOOZE response network. Let me say something about INO. This is a detector at INO In India, iCal is this iron-based detector that will be underground with 50 kilotons of iron. This detector is probably not too sensitive to the very low energy neutrinos from a supernova burst. However, one thing that could be possible that would be very exciting is following the supernova, following this initial brilliant burst, there's likely also over the time scale from days or months or years, high energy neutrinos that follow, not in a burst, but over maybe a year. And a detector like iCal could potentially, and actually any of the detectors in the list, could potentially see this late flux of neutrinos from a supernova, which would also be really, really exciting. Okay, so just to end here, I want to mention here, just to make sure everybody knows this, that the neutrinos are coming. And here's a way of thinking about it. The Milky Way galaxy is about 650 light centuries across. That's how long it takes the light to come from the other side of the galaxy. It's about 650 centuries. And so what that means is that within that horizon, about 2,000 core collapses have already happened, and the neutrinos are on their way. And of course, it will take 650 centuries for them to get here, but they are on their way. And some of them may actually be nearby. The neutrinos are definitely coming eventually, and we have to be ready for them. It's really, some people think that because a core collapse supernova is only supposed to happen every 30 years, then that's too boring to wait. Why should I wait 30 years? The way I think is, that's the wrong way to think, is you have to be absolutely ready to gather every possible bit of information once a supernova has gone off, because you're only going to get one chance, or maybe two in your lifetime, but it's so rare that you have to be ready to capture all the available information. So we really need to be ready for the next supernova. Okay, so here's the summary. Is the next birth of a neutron star or a black hole in the Milky Way is going to be heralded by this brilliant flash of neutrinos, and we're ready now with our vast vats of underground liquids. We should be able to see them. If you sign up, you can be among the first to know that a burst was detected. And now the thing that's going to change in the future, so currently we're sensitive mostly to antineutrinos, but these detectors I'm talking about for the future are going to give a bigger and richer signal. They're going to have different flavors. That's what we'll see in argon. And there's actually also now a whole field of what's called multi-messenger astronomy. There's gravitational waves. There's all kinds of other channels. And all of these can work together to get the best science out of the next core collapse. And the neutrinos are really coming in our future, our multicolor future of supernova detection. So that's all. I'll stop there.
Thanks, Kate, for that engrossing talk. We take some questions.
Sure, yep.
Okay, so if you have some questions, raise your hand. There are a couple of volunteers here who will take mics around. Okay, come. Here.
Good evening, Professor. So my question was, how do you differentiate between neutrinos and antineutrinos in a detector?
Oh, that's a great question. That's not easy. It depends on the detector. The water detectors you can actually distinguish, and in fact SuperK is being upgraded, we can do this better, is antineutrino interacts with a proton, a neutrino interacts with a neutron. So if you've got free protons in your detector, you mostly see antineutrinos. So it interacts with a proton and it makes a neutron, and if you can see the neutron, then you can, we call it tag, you can tag the interaction as an antineutrino. And so that's something we should be able to do. In Dune, you can also look, you can't do the same kind of tagging, but you know that it's mostly neutrinos that have the biggest probability of interacting. But there are subtle things you can look at in the event that can help tell you whether it was a neutrino or an antineutrino. For some kinds of interactions, you can't tell the difference, but for the big detectors, you can actually do a reasonable job.
Thank you, Professor.
Okay. Yeah.
Why doesn't the why doesn't the Pauli exclusion principle stop the supernova from becoming a black hole?
So that's okay, the Chandrasekhar mass is actually the maximum mass at which that works. And then once it gets heavier, it's called degeneracy pressure, can no longer hold up the star. And then you will eventually create eventually the overlying pressure overcomes that degeneracy pressure, and you will get a collapse.
Yeah.
So, good evening, Professor, first of all. And I wanted to ask that can you put light on the supernova explosion?
I'm
When
sorry?
the supernova explodes, the heavy elements are formed.
Yes.
So, can we detect the elements? What can be they, and what will be the atomic masses? Would it be the new elements outside the periodic table?
Yeah, so there will be elements from nucleosynthesis in a supernova. We can probably, actually some of that you may learn about from the actual later explosion rather than the neutrinos. There may be some information about you can learn from the temperature of the neutrinos, that and the temperature of the electron neutrinos versus the antineutrinos. If you can tell apart those temperatures, it may be possible to learn about which nucleosynthesis processes are happening in the star. It's not direct, but you can get indirect information. I think it's actually now thought that a lot of nucleosynthesis really happens in mergers of black holes. There's been these gravitational wave detections you may have heard about, and there's actually evidence now that a lot of mergers of, I should say not, there have been gravitational black hole mergers, but neutron-star merger, evidence from that has indicated that there's possibly a lot of nucleosynthesis happens in an accretion disk that's consistent with the observations of that. And so supernovae, there's certainly going to be some nucleosynthesis. It might not be the dominant kind of nucleosynthesis. Yep.
Does it say that the neutrinos can be detected first by the light? The light of the supernova, as the explosion comes, it comes after the neutrinos.
Yes.
How can that be possible? We say that the light is the fastest traveling thing.
Yeah, it's not because neutrinos go faster than light, because they don't. It's because the photons are trapped. Photons, because neutrinos don't interact, they just zoom right out of the star. But the photons, if a photon is created deep inside a very dense object, it will bounce around, it will get transformed. For instance, the photons created in the center of the sun take literally 1 million years to get out of the sun. And so the photons, you really have to wait for a shock wave to come out of the explosion and heat up the layers that are not too dense for the light to escape to infinity. So it's really because photons are trapped and neutrinos are not.
So it's not the speed of
It's not the speed of the particles, yeah. In fact, neutrinos are a tiny, tiny bit slower than light because they have a bit of mass.
So my question was, since the neutrinos are more penetrating than light, would it be theoretically possible to create a neutrino equivalent to the CMB using these detectors?
Neutrinos from the CMB, or like?
Basically the neutrinos created during the Big Bang.
The Big Bang relic neutrinos? So that's kind of a holy grail of neutrino physicists. That's very, very difficult because those neutrinos are very, very cold. They are very low energy. And so these neutrinos from a supernova I'm talking about are something like 10 up to maybe 50 MeV. The Big Bang relic neutrinos may be less than 1 AV. So they're very, very low energy. And almost all interactions of neutrinos at those low energies are almost never happen. It's very low rate of interaction. So that's an extremely technically challenging problem. There are a couple of ideas. There's an experiment called Ptolemy, but it still has a lot of technical challenges. You can actually interact with, it's kind of like you have a radioactive nucleus and you interact just as it's about to decay in order to see a signal, but it's really, really difficult. So these detectors will see nothing, would not be sensitive to those CMB or cosmic background neutrinos.
Thank you.
Good evening, professors. My question is, just like electron has a field associated with it, the proton has a field associated with it, does neutrino and antineutrino has any type of field associated with it while it is propagating or it is stationary?
Yeah, I mean, I think you can think of it, actually any particles you can think of as being associated with fields. So yes, I mean, it's a weak interaction. So it's not an electromagnetic field. But yes, you can all particles you can think of as fields as well, yeah.
Thank you.
What may be the percentage of neutron, neutrino and antineutrino produced?
I can't see where this, sorry.
What may be the percentage of neutrino and antineutrino produced?
Produced in a supernova, it's about equal. In fact, all of the flavors are approximately order of magnitude. All of the 3 flavors and their antineutrinos are approximately equally divided in a supernova.
One pure water sample is lying on your table, right? The next step is ultra pure water.
Yep.
Where out of 55.5 crore water molecules, only one ionizes, so you get protons and OH ions. Protons is not free, so they combined with water forming H3O+. These ions you can't escape, however pure it is.
How pure is it? Well, I mean, I call them free protons. That's sort of from a nuclear physics point of view. I mean, not in a nucleus, really. But the water is, I can't remember exactly what it's a resistance number that characterizes it. It's not ultra pure. It's pure enough to be unhealthy when you drink it. But it's. It will suck out ions out of you. So it's mostly for, the reason we want it pure is mostly for radioactivity, is that contaminants are radioactive and that will create signals in the detector. So the reason it's also we want it to be transparent so that we get low attenuation of the Cherenkov light, but it's not for chemical reasons, it's for low radioactivity and for good transparency.
Hello, ma'am. My question was about the detection quality that you talk about that the Super K detectors are detecting like the expected probability is around 1,000 for the galactic center.
Yep.
So can you tell me about any expected rate for our nearby galaxies?
So I think Andromeda is supposed to have about a similar rate of supernovae as the Milky Way, maybe within a factor of 2, could even be a little bit higher. Andromeda is far enough away that we would expect only maybe 1 neutrino in Super K from Andromeda. So it goes down as, goes as the square of the distance, inverse square of the distance, and so it would be a very small signal in Super K from Andromeda, but we might see 1 neutrino, maybe 2 neutrinos, something like that.
So it's very low.
So
It's very low.
it's very low, yeah. And it should happen about the same, maybe also every 30 years or something like that.
So we don't have any GSK for that for K, Super K, or we have to go for other detectors for that?
Yeah, you need bigger detectors to see farther, yeah.
Thanks.
Ma'am, you said that the astronomers usually get an early alert before a supernova. So how early is the alert exactly?
So that's a great question. So it depends on the nature of the stellar envelope. So there's some stars that don't have very much overlying matter, Wolf-Rayet stars, for example. And so in those cases, this shock wave could get out and produce a supernova within, it could be 10 minutes. It could be a very short period of time. It could be less than half an hour, which means we don't have a lot of time for getting the neutrino alert out. But some stars that are very massive and have very heavy envelopes, it could be hours, it could be even a day. And so actually 87A, the delay between the neutrinos and the first light was about 2.5 hours. So that's sort of the time scale that's how much time we have to get that alert out. Our aim is actually to get the alert out within less than a minute. Right now it's probably several minutes, but we are trying to improve that to get it to be very fast.
I have one more question. Like, why do we use ultra pure water in the detectors?
Why do we use pure water?
Yeah.
So it's partly partly is in order to, if it's murky and has dirt in it or contaminants, then we won't get a lot of Cherenkov light.
Why ultra pure water? Like, why not regular? Like, why only ultra pure water? Why not any other material?
Other material?
Yeah, like you said, there were argon detectors and
I think there's many considerations, but water is actually great because it's cheap. Water is, we get water from the mountain in Super K, and it's already fairly pure. You just have to purify it. It's really very inexpensive, so you can make a very big detector. Other detectors are, there's always pros and cons. Argon is, of course, it's more expensive per volume. You have to liquefy the argon, and there's cryogenics, and it's much more complicated.
No, what are the properties of water that enable it to be a detector?
What make it good for the detector?
Yeah.
Good you get Cherenkov light. It's stable. It's safe. I guess you could drown in it, but it's not toxic. It's stable, safe, cheap. You get Cherenkov light. It has the disadvantages are the Cherenkov light is not a lot of light, so you have to worry about it. Particles that are very heavy, you can't see them because they are below Cherenkov threshold. So there's pros and cons in all of the different choices.
And one more thing that you said, there is a detector in Japan. But Japan is a country which is very prone to earthquakes. So is it really safe to plant a detector there?
It's prone to what?
Like Japan
earthquakes. Yeah, great question. The actual region of Japan it's in is actually relatively stable. Of course, it's something that the engineers who are designing the cavities have to worry about. But actually, that area in Japan is not so bad. Actually, we had the beam experiment where the beam comes from Tokai, which actually suffered very badly from the earthquake in 2011. And that was actually a delay of about a year. We were very lucky; nobody was hurt who worked in the experiment. But that is a worry. We have to worry about seismic activity. But that actual mine in that area is not especially dangerous.
Thank you.
Yeah. All right. So you said that 99% of the energy from the core collapse goes into the neutrino, and also that it's 500,000 times less massive than electrons. So I'm assuming it's coming really fast when it hits the detector. So if the mass of the star is less, the energy would be less, so the speed would be less, and you would get more detection from a less massive star?
No, actually you get more from a more massive star usually. So the mass of the neutrino is actually only a tiny fraction. The rest mass of the neutrino is only a tiny fraction of the energy of the neutrinos. It's mostly the kinetic energy of the neutrinos that gets converted. So when the star falls, it converts its gravitational, a massive star has more gravitational potential energy that gets converted into kinetic energy when the star falls. And so you will actually, if it's more massive, you will tend usually to get more neutrino energy going out. Or it's actually usually more energetic neutrinos coming out. So they have more kinetic energy. The rest mass energy of the neutrinos is a tiny correction to that.
And where do you get 200 tons of argon from?
From the air. Yep. Actually, there's another story there is that there's actually radioactivity in argon. There's argon-39, which comes from cosmic rays, and it has a half-life of 300 years. And so you can't wait for it to decay over your lifetime. And actually, that creates some background. And for some experiments, and actually for Dune, it's probably too ambitious, although we're kind of thinking about it. Some experiments that need very low background actually use argon that comes from underground, where it's been away from cosmic rays for hundreds of years, and it doesn't have that radioactivity in it.
Yeah. Ma'am, when I saw the graph of the number of neutrinos we see per every second, I noticed it was it looked like it was exponential.
Okay.
Is it exponential? If yes, what are the reasons?
Which graph that was exponential? The graph of
the number of neutrinos we see per second.
Per second. Let's see, which one was that?
Flux as a function of time.
Which one? As a function? Oh, as a function
of time.
Yeah. Oh, the falling off. Yeah. So it is approximately exponential. It's actually it's a diffusion actually. So I don't think it's exactly exponential, but it comes from, and there's various effects in play, but it comes from, so neutrinos are actually, even though they interact very weakly, they are actually trapped for a short time. The neutron star is so dense that they are trapped, and the timescale that drives that is the timescale for diffusion of the neutrinos out of the very, very dense matter. So it comes from diffusion.
I think we will stop now and take discussions over tea. Maybe one last question here, red shirt. Spider-Man.
Good evening, ma'am. As you and we all question about neutrinos. So if in future we get control of neutrinos, how to use them? So where possibly in real life we can use them?
In real life, use them. Okay, so I don't have any good ideas. So there are actually uses for neutrino detectors. In fact, neutrino detectors actually in the same energy regime as supernova detection can see antineutrinos from nuclear reactors. So that's actually a use that people have been exploring, is for monitoring, for nuclear nonproliferation, or you can tell if a reactor is running or not from outside the reactor by looking for the neutrinos from it. There have been ideas floated around for neutrino communication. You could actually use neutrinos in principle for communicating through the Earth, for example. But in practice, you need such enormous detectors that it's not really practical compared with other ways of communicating, like your cell phone. So it's so far that kind of use hasn't really worked out as a viable thing.
Thank you.
Okay, with that, let's end the session. Let's thank Professor Kate Schulberg again. And before we leave for the tea, I would also like to thank everybody who helped in making this program and this lecture series a success, starting with Monica D, who is here, the auditorium staff, members of TIFR, who have been very helpful in making this happen, and thanks to all the audience who were here, very patient and very interactive. For you, there is tea and some snacks. Just go outside, turn right, there is a gate, and you will see a queue of people. So just join the queue. Thanks.